Good morning, good afternoon, good evening. This is STAT 248, the second video of the course. In this video, we will look at Markov chain Monte Carlo methods. So in the previous video, we talked about perfect sampling methods such as rejection sampling or transformation, like inverse transform sampling. And we talked about importance sampling. Those are the classical Monte Carlo methods, along with Markov chain Monte Carlo methods, which is the topic of today. So this class of methods consists in generating a Markov chain and not sampling IID from a proposal distribution. So that's the main difference. So we will first look at this general principle of Markov chain, of the use of Markov chains to approximate probability distributions. And we will ask the question of convergence. So how many iterations will be necessary? Which will be a topic we'll go back to in much details in the later part of the course. In a second stage, we will talk about some specific algorithms, like some of the most classical algorithms called Metropolis Hastings and Gibbs sampling. And then we'll see some concrete examples of how those algorithms can be employed or designed to approximate certain distributions of interest. And that's the plan for today. So in the last lecture, we've looked at Monte Carlo methods, which are essentially randomized algorithms in the way that they have inputs, outputs, and they use random variables to produce a random output. And those algorithms are designed to approximate a target distribution denoted by pi. So the distribution pi is what we want to approximate. The output of the algorithm are points x1 to xn that are on the state space. So here are some points x1, x2, x3, x4, x5. And we can associate a Dirac mass on each of those points. A little vertical bar called a Dirac point mass at those x's, named after Paul Dirac. And then the average of those Dirac masses, also called the empirical distribution of those samples, converges to the target distribution as the number of samples goes to infinity. So that's what we want from a Monte Carlo algorithm. And also sometimes we might have weights associated to the samples, like in importance sampling. So not all samples are necessarily equally weighted. They can have unequal weights. But either way, in the methods that we've seen so far, we have generated those x's, those samples x's, independently of one another, either directly from pi using rejection sampling or inverse transform sampling, or from a proposal distribution Q in the case of importance sampling. So either way, we generated the samples independently of one another. So what we're going to look at next is a set of samples generated by a Markov chain, which means that we're going to generate first x0, and given x0, we're going to generate x1, so using x0. Now that we have x1, we're going to generate x2, given x1, and so on and so forth. So the samples that we're going to generate are not going to be independent of one another. So the big benefit of Markov chain methods for Monte Carlo, for the approximation of probability distributions, is that we will not need to know a global approximation of the target pi. Remember, in rejection sampling and importance sampling, we needed an approximation Q of pi that was a good approximation of the whole target as a whole, right, of the entire distribution. Well, here with Markov chain Monte Carlo, we will not need such approximations. So let's talk about Markov chains in general. So Markov chains have been introduced
around the early 20th century by Markov, who was looking at the law of large numbers and whether it could hold without having IID samples. So let's look at a Markov chain. So let's draw an axis for time or iteration horizontally, and the state space here is the real line, say, on the y-axis. And we're going to draw a trajectory, so x0, x1 at time 0, 1, 2, of points, and we see them moving around. So you see x2 and then x3 seems to be equal to x2, but then x4 is different from x3. So sometimes the Markov chain might move, sometimes it might stay wherever it was, but it's at least moving forward in time. And eventually, after capital T steps, we get xt. So the Markov chain is generated according to what's called a transition kernel, a Markov transition kernel. That means that xt given xt minus 1 is sampled from a distribution k xt minus 1 dot, also denoted by k dot vertical bar xt minus 1 or x xt minus 1 arrow dot. So k stands for kernels, and those are just notation for a distribution that can depend on xt minus 1. So the specificity of Markov processes is that if we look at the distribution of xt given the entire past, x0, x1 up to xt minus 1, then this distribution only depends on the most recent state, xt minus 1. So given xt minus 1, we don't need to know about the previous states in order to describe the distribution of xt. Okay. So the main point here for the purpose of this course is that for certain choices of Markov kernel k, we can have the convergence of x capital T to the target distribution pi when t goes to infinity. And thus pi, the target, can be the limiting distribution of a Markov chain as the time step t goes to infinity. And this suggests a Monte Carlo method. If we want to approximate the distribution pi, perhaps we might be able to design a Markov chain, so to design the transition kernel k of a Markov chain, such that the Markov chain converges to pi. And so then, in order to approximate pi, we will simply run the Markov chain, generate the Markov chain, a certain number of steps. And that will be, of course, the key question is how many steps, and collect the last samples. And interestingly, this validity will occur irrespectively of the starting point x0. And furthermore, not only the xt goes to pi as t goes to infinity, but the average over the trajectory of the chain of the delta masses supported by the states of the chain might also converge to pi, which typically is called an ergodic theorem. So from one trajectory, we can approximate pi. So there is a difference between the ergodic average and the long-run averages. So those are ergodic averages. And the convergence of the marginals. So in particular, traditionally, what people do in MCMC is they run long chains. They might look like this following drawing. So you can see the Markov chain moves around when time goes on. Typically, you would discard the first bit of the Markov chain because you think initially you haven't started the chain at stationarity. So from pi, you have started from an arbitrary state. So you'll discard the first bit. It's so-called warm-up or burn-in phase of the Markov chain. And then you would collect the states after the burn-in. And each of those states would be assigned the same weight, 1 over capital T. And if you have capital T states after the burn-in, and then this average of Dirac masses approximates the target distribution pi. So this is the so-called iterative justification of the Markov chain method for Monte Carlo. But it's worth pointing out that there could be another way of using the exact same Markov chain algorithms for Monte Carlo purposes. So in this way, here called the short run method, you would have the same type of diagram. So the x-axis is time, y-axis is the state space. You start from some x0, and you draw a Markov chain. You obtain at step t the state xt. But then what you could do is stop there and start again. From x0, draw another trajectory, obtain another xt. We can call it xt prime, and then start again, and do that many, many times. Of course, it's advantageous on a parallel computing device, because you might be able to produce all of those trajectories completely in parallel, so for the same time. So then what you can do is collect the states at time capital T, denote them by xt1 to xtr, where r denotes the number of replications that, again, you can generate in parallel. And then you could average the states xtr for all the replicates r. Right? So you just collect one time step from each of the trajectories and you average over the number of trajectories. And that also would approximate pi, because this would, by the law of large number, approximate the marginal distribution of the chain at time capital T, denoted by pi t. So the first approximation here is, you can think of it as the law of large number for independent copies. And the second one is that the law of xt at time t is close to the limiting distribution, which is pi, if the Markov chain converges. So now let's look at those Markov transition kernels denoted by k and see what they might, how they might be represented in practice. So those Markov transition kernels describe the distribution of the Markov chain xt given the previous state xt minus 1 of the Markov chain. So it's a conditional distribution indexed by xt minus 1, by the possible states of xt minus 1. And so each MCMC algorithm corresponds to a certain choice of Markov kernel k. In other words, if you specify the Markov kernel k, you specify the algorithm. Even though in some cases it might be described as a pseudocode, in other cases it might be described as a distribution directly, but it must be the same thing. So let's look at particular examples. In discrete state spaces, in particular in finite state spaces, k is a matrix. It can be represented as a matrix, where the entry ij would be the probability that xt is equal to state j, given that xt minus 1 is equal to state I. So denoted kij. So ith row, jth column, for example. You don't have to use that convention, but if you use that convention, there's a nice notation that follows that is very similar to the, that is very amenable or adapted to the linear algebra notation. So for example, you can write the distribution of the chain at step t, pi t, as pi t minus 1 times k, where pi t and pi t minus 1 are row vectors, and k is a matrix. And this equality simply means that the probability that xt is in a state j is equal to the sum over all possible states for xt minus 1 of the probability of transitioning from a state I to a state j times the probability of having been in state I at the previous state. So this is the law of total probability written for one step of the Markov chain. But conveniently, it can be written also in linear algebra as a row vector times a matrix multiplication. In continuous spaces, you can use very similar notation, or even you can use the same notation. And strictly speaking, for example, this equality would mean that the probability pi t of dxt can be written as the integral of pi t minus 1 dxt minus 1 times the transition kernel describing the probability from xt minus 1 to dxt. And that's an integral over xt minus 1 over the entire state space. So we can write this also using the linear algebra notation, even though here it's on continuous state spaces. So pi t equal pi t minus 1 k. And also we will write the iterate of this kernel as, for example, pi t equal pi 0 times k to the power t, which means the k to the power t describes the tth transition, the transition over t steps of the Markov chain. And again, in the case of finite discrete state spaces, it's equal exactly to the matrix power. So let's look now at some examples of Markov chains. So we're going to look at a first example where x0 starts from the state little x0 arbitrarily in the state space. Let's imagine a value in the real line. And then define xt to be xt minus 1 plus epsilon t, where epsilon t is normal 0, 1, and all the epsilons are independent of one another. So this is a very standard random walk on the continuous real line. So let's try to see if this Markov chain converges or not. We can write x1 as x0, which is a fixed value, plus epsilon 1, which is a normal 0, 1. And so marginally x1 is a normal x0, 1. And we can also compute the marginal distribution for x2, and so on up to xt, which is a normal with variance equal to t. And so as t goes to infinity, the variance explodes. And so the marginal distribution is normal for any time step, but in the limit, it's like a degenerate normal with infinite variance. So there's no proper probability distribution that in fact correspond to the limit, to the limiting distribution of the Markov chain as t goes to infinity. Okay, so this is a Markov chain that doesn't really have a limiting distribution, not a proper one at least. So next we can look at another example, maybe a more favorable example, more representative of what we're looking for with MCMC. We start again from an arbitrary value, x0, and this time we define xt to be rho times xt minus 1 plus epsilon t, where epsilon t is as before, that is independent normal 0, 1, whereas rho is a value between minus 1 and 1 excluded. So then, if we do the same type of calculation, we find that x1 is marginally normal rho x0 variance 1, x2 is mean rho square x0 and variance 1 plus rho square. And if we do the calculation iteratively, we find xt to be a normal with mean rho to the t x0 and variance 1 plus rho square plus rho to the 4 plus all the way to some power of rho. And so this time we can take the limit. When t goes to infinity, we find that the mean would go to 0 and the variance would go to a fixed value, namely 1 divided by 1 minus rho square, if I'm not mistaken. So that's a normal distribution, a proper one. And note that the mean and the variance converge geometrically fast, right? With exponent, with coefficient rho. And that is quite typical, in fact, of Markov chain Monte Carlo. And so in the context of Monte Carlo, we will try to design a Markov kernel K in such a way that the resulting Markov chain admits the target distribution pi of interest as the limiting distribution. Okay, so the goal the target distribution is the objective, is the goal, and the way of approximating this distribution will be via a Markov chain if we manage to design the Markov kernel K appropriately. In such a case, the marginal distribution of the Markov chain, pi 0 k to the t, so that's the distribution of the chain after t step of the Markov kernel started from pi 0, might go towards pi. So how do we design such a kernel? So one idea is to follow a fixed point iteration procedure. So this is a very classical idea that dates back to the Babylonians, in fact, 1700 BC. There are traces of algorithms to compute the square root of a number a by defining an iteration with a function f of x equal to half of a divided by x plus x, and then defining a sequence starting from an arbitrary x0 and recursively defining xn as f of xn minus 1. So you can note that square root of a is the fixed point of this recursion. So f of square root of a is square root of a. And then the resulting sequence, xn, can be shown to converge to square root of a. So that's one example of many fixed point iterations that have been the topic of analysis by many people, in particular in the 20th century, Banach, Brouwer, or the Italian mathematician Cacciopoli. So the idea here is to define a fixed point recursion, so a recursion such that the object of interest constitutes a fixed point. So is invariant by one step of the recursion. So in the context of a Markov chain, this could mean that we're looking for a recursion such that if the Markov chain was distributed according to pi and we did one step, the next step will still be distributed according to pi. And then we would say that the kernel K leaves pi invariant, or is pi invariant. So if we manage to construct a recursion that is a Markov kernel K that leaves pi invariant, in other words, that can be seen as a function taking pi and outputting the distribution after one step, and if that would be equal to pi, then possibly the iterations would converge to that distribution pi. Okay, so that's a principle, fixed point iteration, but that still doesn't tell us exactly how we're going to design the Markov kernel. So how are we going to design a Markov kernel K such that it leaves this pi invariant? So now we're looking for a Markov kernel K such that doing one step of this Markov kernel would leave the distribution pi unchanged. So we'll note that something called reversibility implies pi invariance. So what is reversibility? Reversibility of a kernel K with respect to pi means that pi of x k of x to x prime is equal to pi of x prime k of x prime to x for all x prime. Here the equation assumes that everything has a density, or if you think of discrete state space, then the equation makes perhaps more sense than continuous state spaces. So this equation, if it is satisfied, then K is pi invariant. So we can check that in just a couple of lines. Indeed, we can integrate pi of x k of x to x prime with respect to x. Using reversibility, we can basically switch x and x prime within the integral, but we're still integrating with respect to x. And so we can take pi of x prime out of the integral, and we're left with the integral of k of x prime to x, which is equal to 1 because for any x prime, k of x prime to x is the density probability function of a distribution, and so integrates to 1. And so thus, pi k is equal to pi if k is pi reversible. And that's what we're going to do later on. We're going to design k to be pi reversible. And that leads us to the Metropolis-Hastings algorithm, which is really derived by trying to make a proposed Markov chain reversible and coming up with the adequate modification of the original Markov chain. So namely, from a given state xt-1, we will propose x star from a proposal kernel, so just a distribution indexed by xt-1. So that would be like a random walk, for example. And then the novelty here is that we're going to either accept or reject x star. That is, we're going to set xt equal to x star, or we're going to set xt equal to xt-1. Either one of those two things will happen with a certain probability. So again, xt is equal to x star is referred to as the acceptation, and xt is equal to xt-1 is referred to as the rejection of the proposal. So we're going to accept with probability denoted by alpha of xt-1 and x star. So it's a function of the previous state xt-1 and the proposed state x star. So it's worth noting that, of course, if we want the resulting chain to convert to the target pi, we need to plug some information about pi somewhere in this procedure. And so it could be in the way that we propose x star, so in the design of Q, or /end in the Metropolis acceptance alpha subscript mh, the acceptance probability. So typically, at least in the most naive versions of the algorithm, Q doesn't look at anything to do with pi, but alpha includes pi in its computation. We're going to see some examples very soon. So basically from x0 we propose x star, maybe we don't accept it, so we stay. So x1 equal x0, x2 equal x1, x3 is accepted, is a proposed point that is accepted, x4 is also a proposed point accepted, x5 looks like it's equal to x4, and so on and so forth. So the chain either moves or stays where the previous state was. And so on. And so after capital T step, you get x capital T. And so the question is, can we set up the acceptance probability for at least some choices of Q in such a way that the acceptance mechanism is going to correct for the discrepancy between the proposal and the target in such a way that xt goes to pi. And ideally, for very generic choices of proposals, because maybe contrarily to importance sampling, we don't want to assume that the proposal is very knowledgeable, very well chosen. So we really want to see if we can compensate for the naivety in the proposal by accepting and rejecting with the right ratio. So note here really that Q is can be understood as a local modification of the previous state xt-1. So the proposed point x star possibly is very similar to the previous one, but a bit different. And we really count on the acceptance rejection mechanism to compensate adequately so that the chain follows pi eventually. So how are we going to design the acceptance probability? Well, as we saw before, if we prove reversibility, we have pi invariance. So maybe we can figure out the acceptance probability, what it should be for the chain to be reversible with respect to the target pi. So the probability of accepting a move first can be computed as the integral with respect to the proposed distribution of the acceptance probability. And so this integral is equal to the overall probability of accepting a move given the current state x. It's an integral with respect to the proposed state. So we haven't specified yet the acceptance probability, but we're going to try to figure out what it could be in order for the chain to be valid, that is, to converge to pi. So the probability of rejection is, of course, 1 minus the probability of acceptance. And given those expressions, we can write the transition kernel K in terms of the probability that the chain started from state X would go to a set, a measurable set A in the state space. So we move to A either by accepting a proposed point in A. So this is the first part of the expression being written here. So an integral with respect to the proposal of the acceptance probability and the indicator that the proposed point is in A. And then there's another component, which is if the proposed point is rejected, so if we're in the case of a rejection, then we could still visit A if the previous state was in A, because the next state will be equal to the previous state. So let's check now that with this expression of the kernel K, we might have reversibility, at least for certain choices of the acceptance probability. Of course, we will have to choose the acceptance probability, alpha, appropriately. So if we want reversibility, it should hold for x prime different than x in particular. And so if you look at the expressions, simplifying because the indicators sort of disappear, what we need is that pi of x, q of x, x prime, alpha of x, x prime is equal to pi of x prime, q of x prime x, alpha mh of x prime x. Right? So it's kind of just flipping the x and x prime states. So we just need to find examples of acceptance rates such that this equality holds. So in fact, there is more than one choice. There is more than one valid acceptance probability in Metropolis Hastings. So the most standard one, the most classical one, which also happened to be a good choice in terms of asymptotic variance, is to set the alpha xx star here as the minimum between 1 and the ratio pi of x star q of x star x over pi of x q of xx star. I just also write down another valid ratio, which again lead to a Markov chain that also converges to the target distribution pi. But in fact, according to a result by Peskin in the 70s, leads to a chain that is always less efficient. So the asymptotic variance is larger for a given proposal distribution Q. So there are multiple choices leading to the kernel K being pi reversible. You can check that indeed those choices lead to pi reversibility. And then pi reversibility, as we've seen before, implies pi invariance. So implies that pi is a fixed point for the evolution of the chain, the recursion that corresponds to the Markov chain. So perhaps by a fixed point iteration argument, we haven't actually mentioned any of the required assumptions for the fixed point iteration to converge, and of course there are some assumptions, but under some conditions we might hope that xt will converge to the fixed point distribution pi. So in other words, starting from any initial distribution pi 0, doing t-step would lead to a marginal distribution that converges to pi as t goes to infinity. So of course there must be conditions. Right? There must be conditions. In particular, you can easily see that there should be conditions on the proposal distribution Q. For example, if Q was a Dirac mass on the current point, then the chains will never move. Right? So it has to be more than that. We can look at a toy example also to see that we need more than just trivial assumptions. So for example, we can introduce a target distribution on the real line with two modes that are completely separated. So what is plotted here is the density function of a target distribution pi. You see it has two modes, two regions that have a non-zero probability under the target. And they're separated by a gap. Right? And so imagine that our proposal distribution is the uniform distribution around the current point, x, with a certain radius epsilon. So we can write q of xx star to be the indicator function that x star is in an interval, divided, if we want to normalize, divided by the width of the interval. Then, of course, in that particular case, if the width is too small compared to the gap, then the chain cannot move from the left-hand side to the right-hand side of the support of the target. And so we cannot expect the Markov chain xt to converge to the target distribution pi. So we've looked at Metropolis Hastings. Another really big idea in MCMC is Gibbs sampling. The idea that dates back to perhaps the 50s, 60s. It's not clear who came up with it first. To explain this idea, we need to have a target distribution pi on a multivariate state space where x can be decomposed into blocks x1, x2. They could be univariate or multivariate, but we're just labeling two sets of components, x1 and x2. The idea of the setting is that we might have access to a Markov kernel, denoted by K1, that leaves the conditional distribution of pi, under pi, of x1 given x2. So pi of x1 given x2, invariant. So it's like an MCMC algorithm itself, K1, but operating for a fixed x2 and targeting this conditional distribution. From that, we can extend the Markov kernel K1 into a joint space of x1, x2. So we write K1 bar as a kernel that leaves the x2 component unchanged. So x2 prime will be equal to x2 with probability 1. That's a Dirac mass on x2. And then combine with a Markov kernel that we introduced, K1, that operates only on x1 and that targets the conditional distribution of x1 given x2. Then this K1 bar leaves the whole target pi invariant. It doesn't move x2, and that's also useful in proving that K1 bar leaves the whole distribution pi invariant. And so likewise, we could introduce K2, leaving the conditional distribution of x2 given x1 invariant. So here, K1 might depend on x2, and K2 might depend on x1, because we're conditioning on those components. So then the idea of a Gibbs sampler is to generate a Markov chain on the whole space of x1, x2 by alternatively sampling from K1 bar or from K2 bar. So we're gonna, whenever we sample from K1 bar, we're gonna update the x1 component of the chain. And when we're sampling from K2 bar, we're gonna update the x2 component of the chain. And so overall, of course, we need to update all of the components of the chain if we want the chain to converge to stationarity from an arbitrary starting point. So that's the idea of Gibbs sampling, and there's a lot of open questions still around Gibbs samplers. So for example, about the order of the updates. We could either systematically scan the components and update them, for example, component 1, then 2, then 1, then 2, then 1, etc. Or we can also have 3 updates of component 1, then 1 update of component 2, 3 updates of component 1, 1 update of component 2. Or we can employ a random order. And when we employ a random order, so we flip a coin to decide which block to update, and we can use equal frequencies or not. And so this is just Gibbs sampling for 2 blocks, but it's easily generalized to arbitrary numbers of blocks. And so the really nice idea of Gibbs sampler is to update smaller dimensional components at a time instead of operating necessarily on the joint space. So we're going to look at the difference between the joint space and component-wise updates in an example. So let's look at a bivariate target distribution. Those are the contour plots, so indicating like the map of a mountain, indicating the different levels of high density here near the origin. So we imagine here this Markov chain where some points are proposed and some points are rejected or accepted. So this is Metropolis Hastings with a proposal distribution that is itself a bivariate distribution. You can see that the proposal can be modified from the current x by modifying both components, the x and the y component, or the x1 and the x2 components. So for example, the chain that is drawn here could correspond to Q being a normal distribution centered at the current state, for example, and with some certain covariance matrix. So that would be a Metropolis Hastings with a joint proposal distribution on the entire component. But a Gibbs sampler, on the other hand, if it starts from some x0, it would, for example, only modify the x2 component first. So you would move on another state that is on a vertical line going through x0. And then if you update again the x2 component, you'd remain on that vertical line. So of course, you need to alternate between the two components if you want to ever move out of that particular line. And so after updating the x2 component, you'll start updating the x1 component, and then you move on a horizontal line for a fixed x2. So it's allowed to do that as long as you're leaving the conditional distribution of either x1 given x2 or x2 given x1 invariant when you do that. So in terms of trajectories, you can see that if you do that, you end up with sort of staircase trajectories. So only horizontal and vertical moves. So what's the benefit of doing this? So it looks like it's just an additional constraint to be able to move only on 2 axes instead of moving anywhere. But the benefit of Gibbs is really not to be underestimated, is that it decomposes the original d-dimensional problem. So here it's only 2-dimensional, but it could be very large dimensional. It decomposes this original problem into possibly a lot of small problems. Right? Remember, you can do it with 2 blocks, but also any number of blocks. So for example, you could do it by decomposing d components into d one-dimensional. So now, to wrap up, let's look at some examples, some typical settings that you will find in many articles on MCMC, where we can illustrate Metropolis Hastings and Gibbs sampling. So the first one is Bayesian logistic regression. So this of course a regression problem, so that's inspired by statistics. Here the outcome, the variable outcome, is binary. For example, it's 1 if the passenger of the Titanic survived, and 0 otherwise. And x is the covariates. So we have a vector x for each individual, each passenger, for example, which is a d-dimensional vector of features or covariates, such as age, gender, for example, indicators of the class, so first class, second class, third class, associated with each passenger. And you might want to see how the probability of survival is associated with the covariates, how it depends on, for example, age or the class of the tickets. So the logistic regression stipulates that the probability that y is equal to 1 is the exponential of x transpose beta divided by 1 plus exponential x transpose beta, also called the xpit function of x transpose beta. So it's a linear regression because it's x transpose beta, but it's transformed to take values in the interval 0, 1 so that it could represent a probability. So in the Bayesian inference, we would be interested in the posterior distribution of the regression coefficient beta, obtained as the prior, for example, some Gaussian centered at 0 with some variance, multiplied by the likelihood, which is a product over the n individuals of a Bernoulli probability evaluated at the observed y and with this x-bit probability. So for a cost that is of the order of little n, the number of observations, and also, I guess, linear in D, we can evaluate the posterior density up to a normalizing constant for any coefficient beta. And we can also evaluate the gradient of the log posterior density, the gradient with respect to beta. And thus we can implement Metropolis Hastings with a variety of proposals. In particular, random walk Metropolis Hastings, what's called Metropolis adjusted Langevin, Metropolis Hastings, or Hamiltonian Monte Carlo. A lot of research on MCMC on continuous state spaces recently had been on those Langevin, so-called Langevin methods, or discretization of Langevin processes as a proposal distribution and then adjusted with a Metropolis Hastings step, where beta star is sampled from a normal centered at the current beta, but following also the gradient with a step size h and a certain covariance sigma. So we can also think of Gibbs sampler for logistic regression, and we can go back to this in the live lectures. Next example is the Ising model, very classical example that comes from statistical physics. We imagine a grid, an n by n grid, two-dimensional here, and each node in the grid is called a site. So we have an n by n grid with sites, and each site is associated with a variable xij for the ith row and jth column, and xij is a variable that takes two values, either +1 or -1. It could be called a spin in reference to the setting in which those models have been introduced by Ising. So X is the ensemble of the sites, so the whole grid with +1s and -1s. And so it takes value in -1, 1 to the power n cross n. So it has a cardinality 2 to the n times n. So even for moderate values of n, it's impossible to enumerate all the possible grids. And so it's not easy to sample from distributions on grids. And so the distribution that we'll be looking at here, which is the simplest in the class of Ising models, is proportional to the exponential of some constant. We'll think of a positive constant here, but it could be negative in principle also, times the sum over all neighbors of xij times the neighbor of xij, over all sites ij and all neighbors of ij. So we multiply the values, which means that if they are the same sign, we get a +1. If we get a -1 if they are of opposite sign. So for example, we can imagine that the site ij has 4 neighbors in this configuration. There are also one-dimensional or three-dimensional versions of this model with different numbers of neighbors. So what this target means is that it prefers grids where nearby sites have the same spin, to the same value, either -1 or +1. So it encourages grids where nearby sites, or pixels if you like, are of the same sign or the same color, if you like, to think of it in terms of images. So it doesn't like if every pixel is a different color from its neighbor. That's if the constant is positive and the constant is proportional to what would be called an inverse temperature in the original setting of ferromagnetic, where this kind of model has been considered first. And so a Gibbs sampler here, which would be often called a Glauber dynamic in the context of statistical physics, would update each site one at a time from the, for example, by sampling from the full conditional distribution of the target of that site given all the other sites, which is easy to sample from because it's just a Bernoulli variable. So those are just examples. We'll go back to those examples in the later chapters. But of course, one of the main points in MCMC, one of the main interests is that it's generically applicable, and thus, please feel free to see the notes for other examples, but also to find your own examples that you care about. If you're interested in ecology or sociology or politics, you will find MCMC examples that apply to those fields. Most importantly, implement your own samplers. Right? So once you have the notes and the videos, you have all the ingredients to start implementing some MCMC algorithm. Start from the simplest and then building up from the simplest to more realistic examples. I believe it's really the only way to really understand what's going on is to implement, to code yourself MCMC algorithms. And it doesn't have to take a lot of time actually. Later on, once you'll be familiar with the ins and outs of those kind of methods, of course, it can be a good idea to try statistical software that have pre-implemented MCMC methods. There are many, they are doing a fantastic job, so I don't want to say at all that you shouldn't use them. When I say implement your own samplers, I really mean in order to really understand what the Markov chain is doing and the difficulty or the elegance or the pros and cons of those methods, you really have to implement those methods yourself a few times at least. Otherwise, there's a lot of very good software, JAGS, Stan, Nimble, Birch, PyMC. If you want, and again, I encourage you to do it, to implement things yourself, the first chapter of the lecture notes has some tips regarding implementation that are probably useful if you haven't implemented those methods before.
Okay, so this wraps up today's video. In the next video, next week, we will start discussing the idea of couplings. And again, they're used in Monte Carlo. And this will correspond to the beginning of chapter 2 of the lecture notes. Have a nice week.